Alexei, we're ready to go whenever you want.
Okay. Good afternoon, ladies and gentlemen. We start our session entitled Integrated Approaches to Addressing Global Challenges Facing the Arctic and Boreal Regions. The first speaker is Professor of Forest Atmosphere Interactions, University of Helsinki, Finland, Lena Beck. Lena Beck is working on biochemical cycles and terrestrial ecology linked to climate change in boreal regions. She received her PhD in zoological plant ecology from the University of Oulu in Finland. Her expertise is in forest management, ecosystem climate feedback, and ecosystem services. She has actively been involved in the development of national, European, and global research infrastructures for integrated long-term observations of Earth's system. Professor Beck is the vice chair of the Institute for Atmosphere and Earth System Research, INAR, at the University of Helsinki. This is a very famous institute in the field. She is author of more than 140 peer-reviewed papers in journal and books, and member in the Finnish IPBES panel. She is academician of the International Academy of Eurasian Studies and has been awarded by the Pro Scienta and the Open Science Award. Please, Lena, the floor is yours.
Thank you, Professor Gypsiani, and I'm sharing my screen. Please tell me if you are seeing it.
Yes, that's fine.
Okay, good. So thank you for invitation, and I'm very happy to present in this session because I think that the topic is really important, and what I try to bring to you as a starting point for discussion and maybe thinking about is what is the role of the systematic observations in the Arctic and Boreal regions that are capable of addressing and maybe also answering some of the global challenges and questions that are currently ongoing, but also what we are going to see in the future when, for example, climate change is affecting our regions. I have two co-authors listed here in this presentation, but of course there are many more. The two that are listed here are founding members of PEAKS, Marko Kulmala, academician from the University of Helsinki and Institute for Atmosphere and Earth System Research. And another one is Mikael Mittel from Austria and Germany, who is the key figure of Ilter ESRI, European Long-Term Ecosystem Observation Network, which I will be introducing you in the presentation as well. But first, in a few words, I think that we all are aware, and I don't go into details in what kind of challenges the Arctic and Boreal regions are currently facing. This is just a few examples of anthropogenic and climate change pressures. On the left-hand side figure, the small dots show the anthropogenic activities around the Arctic and northern boreal areas, and you see that there are lots of dots in many places, which shows that there's high industrial interest and high mining interests, for example, occurring in the circumpolar and circumarctic regions. So they are clearly something that is affecting our region already very intensively for decades. The other more current research challenge or global challenge is, of course, the climate change pressure. The figure on the right-hand side shows with a color coding how intensive the climate warming has been over the last 30 decades in these different regions. And the redder color means the more changes have already been occurring. And the vast majority of the changes in the Boreal and Arctic regions, of course, are focused on the Arctic Sea and the regions that are surrounding the Arctic Sea, like the ecosystems in Siberia and northern Europe. So these kind of challenges are requiring the science and society to urgently design good tools how to respond to these challenges. And the thing that I'm suggesting and we are suggesting is that we need urgently to provide systematic and integrated observations on the state of our ecosystems, how people are affecting the ecosystems. There should be dedicated programs and in situ research stations that are capable of integrated approaches to observe, monitor, and research the Arctic and surrounding areas. The map is showing one example of population studies in Arctic biodiversity assessment done some years ago. And here again, the details are not so important, but the colors of the small dots that you might see in your screen reflect the number of populations that have been observed in these different regions. And the striking phenomenon here is that most of these bubbles, small dots, are yellow or orange, which means that the observations on biodiversity assessment have only been done based on 1 or 2 populations only, which is way too little to be able to say anything about how habitats are changing, how the connectiveness of the environment is changing concerning the biodiversity values of the Arctic and Boreal regions. So clearly there is need for increasing the intensity and also the systematic observation schemes. Repeated measurements, of course, are needed to follow up the trends and observe what kind of drivers are affecting the state of the ecosystems. In support to observations on the ground, which is what we do in the Institute for Atmospheric and Earth System Research, of course, remote sensing and satellite observations and other airborne observations are definitely needed to be able to upscale from site-based studies to regional-based studies. And there has been initiatives in recent years towards this direction. So Marko Kulmala was providing Nature commentary in 2018, where he said that we urgently need a continuous comprehensive monitoring global Earth observatory. And this was commented or continued in a dialogue between the Chinese academician Professor Guo Huadong, who is a chair of the DBAR Institute of Remote Sensing and Digital Earth in China, who was also saying that there is clearly need to take the first steps how to maintain, how to investigate systematically the environment. What is existing at the moment is quite promising, at least. I would say that we are starting towards these steps, and here I have a few examples of what is existing in the Arctic and Boreal regions. There is a vast network of stations, field stations. We have they are located in the Arctic and Alpine areas that is hosted by the Interact network. That's a non-profit organization, and there are now currently about 90 stations in the circumpolar region contributing to Interact. A very prominent European example is IIASA, which is the integrated carbon observing system that has tens of stations, both observing the atmospheric conditions and greenhouse gas concentrations, but also the ecosystems and how the fluxes are created and developed in the ecosystems, and the ocean ecosystems as well, which is seen here in this map with these lines that are showing the ship tracks. Then there is Ilter, which is the European long-term ecosystem and socio-ecology research infrastructure that has currently about 400 stations around Europe. About 60 of them are located above the 58 degrees north. So not a huge number, but still significant number. And it is a very well established network already several decades ago, and it's currently in development phase for becoming a European institution and legal entity. And last but not least, and concerning the vast area of east of Europe, is the PEAKS network, which is here in the bottom of the figure. This map is showing the in situ network of stations that have been identified by the PEAKS program as being able to contribute to the observation networks in China, in Far East areas of Central Asia, and then also in many areas in Russia. So it is quite promising, but of course we have to say that there are still huge areas that are not covered by these observations. So by far are we not finished with this creation of this global network. One of the examples of global networks is the Ilter, International Long-Term Ecological Observation Network, that is kind of the parent network of European Ilter. And these dots show you the global distribution of the international Ilter network. By far, Europe is most populated, but there are huge numbers of stations, for example, in Japan, in Australia, in South America, and in North America. But of course, still big gaps existing in the Ilter network, for example, in Russia and in Canada. About 50% of these observations are coming from terrestrial sites, and then the rest of them is somehow linked to waters, either oceans or coastal or fresh waters. Europe has taken steps to formalize this process, and the European ESFRI process is giving visions for development of these infrastructures. Here is an example of the European Ilter network. We have a vision that we will be providing well-being for all citizens, sustainable human interactions with nature, and enabling environment for scientific discovery and insights. So these are great visions, and what we want to do is to address the challenges on biodiversity loss, climate change, eutrophication and pollution, and overall the sustainable management of natural resources, including waters, soils, biodiversity, and ecosystems. Ilter has designed a station network covering different disciplines, and it wants to serve the different research communities by providing basic infrastructure like the stations, but also integrated observations on the geosphere, hydrosphere, biosphere, atmosphere, and human sphere, which is very important in thinking about the Anthropocene and anthropogenic pressures. One example of a comprehensive observation station is the one that I come from. It's located in central Finland. It's called SMEAR station. The SMEAR comes from the Station for Measuring Ecosystem Atmosphere Relations. And what is observed is system structure and functions, the main drivers of the changes, and then interactions and feedbacks between these disturbance effects. And we co-locate and collaborate with many international initiatives. Ilter is one of those co-located infrastructures in our site, and what Ilter provides to sites and also other people and organizations using its services is the registry of long-term observation facilities. So you can go to the DIMES.org and search for sites and search for keywords for parameters, for habitats, for ecosystems. Locate sites in this way. Also, you can locate some data products from a selected repository for time series data. You can do data discovery and visualization. And here is one example of visualization and data contextual information that is derived from DIMES SDR concerning one site in Austria, Central Austria, Töbelboden site, where the WMO Cordex project, regional climate project, was used as forecasting to forecast the seasonal weather and climate events that will happen in the near future or in the far future. So this kind of services can be provided to sites that are registered in the DIMES and providing some basic information on the sites. And my last slide is about the global perspective once more. So as I said, the in situ observations are really important, providing the necessary parameters, but they can be much more when they are connected to the global organizations. And what Ilter has done and the International Long-Term Observation Network is done is that it has connected to GEO, the Global Earth Observation Network, that is observing from remotely sensed data. We are providing the verification and calibration for parameters that can be observed and then scaled with the help of the GEO services to use be able to use, for example, in global terrestrial observation systems. And this is all I had to present. Thank you for your listening.
Thank you very much, Dr. Beck. Let's work in the following way, if you have no objection, that we will have two questions right away after the presentation, and then the other questions will be in the end during discussion. Two questions, please. Who would like to ask something? I would like to ask one question. I visited SMER flagship station in Hautala. That was just before a pandemic came. And I was really impressed by the idea and by its realization. How all those observations, facilities, activities like ICOS, Ilter, Astris, Actris, CEOs, how they are linked to SMER?
Okay, that's a very good question. The key word here is the co-location. So our SMER station is providing kind of, maybe you could call it a skeleton or a framework where these different kind of initiatives and research infrastructures can cooperate. And for example, concerning ICOS and the Ilter, there are a lot of common parameters like soil moisture or soil temperature that are needed for creating the comprehensive observations for both. So it's no need to make them duplicate. We can do it once and use it for different user groups and for different purposes. So this is our way of doing things cost efficiently and also integrate the different disciplines and different organizations so that they can effectively use the data and services that are provided by the station.
I noticed that the activities of SMER are closely linked to INAR, where you work, and doctors of Kulmala, a friend of mine. So do all those networks you listed, like IIASA, Ilter, etc., they are also linked to INAR, or this is rather international?
They are international organizations. INAR is an institute at the Helsinki University. So it is like a department or a faculty at the Helsinki University. It's an internal structure that we have. And it is also very, very multidisciplinary organization. So it covers disciplines from physics and chemistry and atmospheric sciences to limnology and forest sciences, plant sciences. It is, as university departments are both active in research, but also education, and also addressing the societal challenges like climate change, for example. Helsinki University has made a strategy where it has nominated or identified key research challenges that it wants its science communities to address. And one of them is, of course, climate change problematics in many kind of ways from many disciplinary perspectives. And INAR is one of the organizations that is doing that in connection to its partnerships with peaks and with IIASA and so on.
Would it be right understanding to say that all those listed networks, organizations, they have their own data centers? At the same time, they provide data to SMER as well, is it right?
That's true. We have in SMER, we have our own data portal, which is called Smart SMER. And that collects all the data that is collected from the 4 different SMER stations in Finland. So we have not only that one that you have visited, but 3 others as well. So this one data portal collects all our data, and then it is connected to the data portals from IIASA or Ilter, so that there is no need to duplicate the data reservoirs or the repositories, but they can harvest from our data portal. And that's also a cost efficiency issue when you don't have to upload all the data many times to different places. But once you have created your own data repository, then the others can link to that and use the services.
Thank you very much. Okay, so we move to the second speaker. This is Dr. Sergei Chalov. He is Deputy Dean for International Relations of the Faculty of Geography, Lomonosov Moscow State University. He received all his degrees from this university. Since 2018, he is an associate professor of the geographical department of LMSU. Since 2015, he serves as vice president and secretary of the International Commission on Continental Erosion, of the International Association of Hydrological Sciences. Since 2016, Sergei is General Secretary of Geography, Environment, Sustainability Journal and head of the Pan-Eurasian Experiment Moscow office. His research interests are focused on sediment quality and quantity, remote sensing application for sediment transport, fluvial processes, stream ecology, and biodiversity. Please, Sergei, the floor is yours.
Thank you very much for excellent introduction. And so I will just go for my presentation now. That's okay. So I would start from the same few words, like to continue the previous speaker, Professor Beck, mentioning that there is this gap in the Arctic domain related to the low quantity of the stations for monitoring on various environmental processes which exist in Russia. And this is mostly the focus of what would I talk in this speech. And the thing related to these gaps in the knowledge are focusing on more terrestrial things, and firstly related to the fluxes which bring together the huge terrestrial ecosystem and Arctic Ocean. And if we look on the Arctic drainage, this is the huge territory, and the main part of this, in terms both of the hydrology and in terms of the lands, are covering by the territory of Russia, and in particular the territory of Siberia. And we can mention that something like 58% of the Arctic terrestrial flux is coming from Russian Arctic drainage. And this territory then even goes to the south up to Mongolian steppe and China. So, and this is in terms of this hydrological perspectives is also Arctic. But there is few things which we should mention when we want to build comprehensive and integrated knowledge. And the first is that this riverine flux to Arctic Ocean, firstly from Siberian rivers, is almost unknown. And this means that we have the big gap in understanding of the very urgent and challenging processes which are related to the thawing permafrost and changes in net precipitation and runoff, which are associated with these general climate fluctuations or climate change. And in following this, we have very vague understanding of on what is the impact of the terrestrial flux into the Arctic Ocean. And generally in this very fastly changing environment, we have to admit that the estimates of the fluvial experts are required to improve fundamental understanding of the land-ocean coupling. And these fluvial experts are almost unknown. And on this photo, you can see that it's very nice reflection of what I said before, is this thawing permafrost on the bank of one of the largest Siberian rivers, the Kolyma River, and very well known in glaciology or in the climatology, but to say the area which is called Yedoma, Dvani Yar in the downstream of Kolyma, which is visually can be seen as the melting, as the shifting area with very fast changes of the bank line during the daytime. So this is during the hot summer season, which came here to this area, and the big flux of the also very important to the biochemical processes in the Arctic of the organic material goes toward the Arctic Ocean. And we have before no really background to estimate this flux, firstly because of there is no well-constrained estimates of the different loads, and the material is carried out by rivers in very different ways, and the point samples, as it's usually done for in geochemistry, are not sufficient to provide us with the knowledge of the flux. And this means that we have a great uncertainties in the particulate and in the dissolved chemicals flux in these huge rivers. And also the final thing which also make the knowledge very comprehensive is that the processes in the deltas remain generally unknown. What's happening with this flux in the most downstream area? And based on this, we are here in Moscow State University under PX umbrella and under its collaboration with different institutions set up a comprehensive monitoring program campaign, which we called Arctic Flux, and this program was started in 2018 with the focus on making new methodological impacts on the knowledge. And on the second side of this story, that we are focusing to provide a regular campaigns with this novel type of the field investigation. And for general knowledge, what we are working with, what these rivers looks like, I will show this photo, which is the Ob River, but it's not the Ob River. Generally, it's only the very small branch of the Ob River, which is only this branch is only 15% of the total Ob River discharge. And then you can imagine that this is the scales. What is the scales of these fluxes? What is the scales of the monitoring which we have to carry out, and what is the generally this system looks like. So, and the four catchments, which are the biggest catchments of the Siberian Arctic, the Ob, Lena, Yenisei, and Kolyma rivers, were, let's say, cut in the main downstream by our monitoring profiles stations, which were aimed to make to take the information about the both hydrology, the water, and the chemistry of the moving matter towards the ocean. And since 2018, we were developing the methodological approach and making the first campaigns. So with the focus that we are not able to carry out the constant measurements, but we are focusing on making the most, to take or to get the most different conditions in terms of hydrology. And here the dots represent these times of our field campaigns, and the blue lines is the water discharge of these four rivers during the these initial stages of these monitoring efforts. And the main focus in terms of the methodological is that we are looking on making the combination between the novel technological advances in the hydrological studies, like Doppler profiles, which make a very full and very detailed picture of the river, with the depth integrated models of the geochemical flux. So, and combining this, we can think about going towards the comprehensive knowledge of this hydrogeochemical flux. And the first results are very promising, which we have, and which are based on the very big data bank of the geochemistry. And the results are summarized briefly on the next slides. What's fundamental knowledge in the Arctic knowledge we can bring from these monitoring efforts. And the first thing which is on the table now is the knowledge about the geochemistry of these rivers. And there are a few things which are clearly seen. The main that's in general, if we take the well-known in hydrogeochemistry enrichment factor, we can say that the rivers in general are not really polluted. But there is the one outstanding river which goes far from the others in terms of their human pollution, is the Ob River, and we clearly see that in terms of the heavy metals and some of the other microelements, the levels of pollution are quite high compared both to these rivers and also to the general world averages. And if we compare the statistics which we have in the database with the other indices like the Clark's, and we can see the variability of particulate chemical elements concentration in the all these four studied rivers. And also the thing which confirmed the previous statement that in general, compared to these world averages, the rivers represent very specific environments, and some of the elements which are related in this case not to any types of the human activities, but mostly to the lithology of these huge catchments are enriched or high in terms of the concentration, whereas there is the big number of the elements which are below the world averages. A similar story goes with the dissolved chemical elements in these fluxes, and we can identify both elements which are related to the human impacts, and again the OP river will be outstanding in this regard, as well as the other elements which are mostly related to the, let's say, natural processes like they mentioned in these red boxes, and this means that there is the very comprehensive integration of the hydroclimatic processes, of the erosion, and of the human impacts on this huge flux into the Arctic Ocean. And summarizing this geochemical part of the existing, at the moment, these 3 years campaign, we can also identify the averages in between these rivers in terms of the enrichment of particulate and dissolved matter in these largest rivers. And then we can have a background to go further on and to come to the fluxes. And this is the way through linking the trace element concentration with the sediment concentration, and these regional types of the relationships we are able now to get. And this is the way forward for such kind of methodological outputs of the study, when we integrate the hydrodynamic and geochemistry, and from the water discharge using the sediment flux, we go to particulate flux by grain classes which are related to the sediment flux, and then we are going to the assessment of their average annual chemical flux. And here the first estimates which are here, so that's the water, and the water to from these 4 rivers to the Arctic is well known in terms of what is how it looks like. So the Yenisei is the leader, but then we go to the elements, and here the situation is much more comprehensive. So the water is not, the water runoff is not completely the leader in this chemical flux. And we are then identify that, for example, there's the huge variability in the particulate matter exists in these rivers, and annual runoff it's extremely high in the Yenisei compared to other rivers, but in other more toxic elements the situation is quite different. And again, there is the big variability between the system exists, and that means that the system is quite comprehensive. But yes, what I said before, that there is the both hydroclimatic impacts and processes, more geological, geochemical backgrounds, and the human impacts affect this distribution. But of course, this is the way, this is the initial years of this monitoring campaign, and we hope that on these maps, which plot the knowledge in the Pan-Arctica, this monitoring effort by our university and our partners will close these gaps a little bit, at least in this hydrogeochemical marine perspective. So with this, I would like to thank the conveners of this session and the organizers for this very important event, and thank you all for attention.
Thank you very much, Sergey. 2 questions, please, if any. Okay, no questions. Thank you very much once again to you, Sergey, and academician Nikolai Sergeyevich,
Yes, thank you.
with whom you presented this very interesting study together. So we come to the next talk. that will be delivered by Florian Kraxner. Florian Kraxner has been the Deputy Director of the IIASA Ecosystem Services and Management Program, ESM, since January 2009. He first joined IIASA in 2001 to work on land use change in forestry. He has been coordinator of various activities in the areas of carbon potentials, benefits through global Earth observation, and terrestrial adaptation and mitigation of climate change. Dr. Kraxner is particularly interested in socioeconomic and ecological sustainability of natural resources. Among other roles, he serves on various scientific boards within the framework of Future Earth, International Union of Forest Research Organizations, and Asian Resilience Center. He is president of the International Boreal Forest Research Association. Please, Dr. Kraxner, the floor is yours.
Thank you very much, Professor Guishani. I hope you can hear me all and see my slides, okay?
Yes, that's fine.
So I simply go ahead. Thank you very much for having me here today. This is a great opportunity to also show, based on my background, a little bit more on what IIASA is doing with respect to boreal forests in the area under consideration here. And of course, this is also highly interlinked with the work we are doing in the IPFRA, you mentioned it, the International Boreal Forest Research Association. So one of the big things is that there is huge expectations from all forests over the world, and particularly from boreal forests, also with respect, but not only, to climate change mitigation and a very long list of SDGs. So let me show here a little bit what we know, how we go about that. Are there novel ideas we can pursue, and how can we do that? I mentioned already that SDGs are very important in the context of forests, and of course also in the boreal forest context. So just to mention a few: no poverty, good health and well-being, clean water, affordable and clean energy, industry, innovation, sustainable consumption, climate action, life on land, etc. But particularly, I would like to have a look at the climate action and the linkage to the forest. We saw already from Professor Beck that, of course, climate is hitting the boreal and polar area very heavily. And we need to learn how to deal with that, but also how we use the forest best in order to respond to this climate change. Unfortunately, we all know that looking at the climate pathways we are on, we are not heading yet into the right direction. We see that, for instance, we have to soon bend the curve very drastically and also move towards the center and end of this century towards negative emissions even. And one question is how we are going to do that. And of course, also here, I will have a look at what the forests could contribute and how. It is important here to understand that, for instance, the national determined contributions are in many countries to a large content based on land, and here based on forest contributions. However, if we accumulate all these NDCs that have been submitted and are voluntary under the Paris Agreement, they only add up to 1/3 of the emission reductions that we have. That means we have to strengthen here very much our ambition, because the UN gap report, for instance, says that if we don't close this gap of this between 1/3 and full by 2030, and this is not even 10 years ago, then it will be close to impossible, very hard to reach the Paris agreements on 2 degrees maximum warming. So what is the starting base in order to address these problems? And starting base is, of course, as always, information. And it's kind of a strange thing, but we do not know globally very exactly what is the forest extent. And the same problem, of course, also exists in the Boreal area. We see here older maps that have been produced quite some time ago. This is a simple map which is about 20 years old already. Then there have been improvements over time, and maybe one important source is here, the science publication from Gauthier, where this all became a little bit more detailed, and more information came up, for instance, with respect to managed versus unmanaged, and here also permafrost being considered, or on the right-hand side, the amount of biomass stored in these forests. However, this is not enough yet. What we did, we moved on and, for instance, combined this also with market and sustainability information, and created the first map on a 1 kilometer resolution that also considers, for instance, certification and the way of sustainable management all over the Boreal forest extent. You can see this here by different colors. The blue is certified, and the red one is managed overall. Not yet enough. The importance here is always that we cannot act in this kind of arena only based on scientific information. We always have to also consider political considerations, sensitivities, but of course also borders. And so we went ahead together with the Circumboreal Working Group and tried to come up with the first politically agreed Boreal forest map. And this was kind of a next step. And here you see the final outcome. And if you are wondering what was the difference to the one before, one example is just here at the border between Sweden and Norway, where the local authorities insisted that not our scientific-based map is correct, but what they dedicated towards managed and unmanaged forests. So we had to correct this in order to be able to publish this in a report, which for the first time included all circumboreal countries, including, of course, Russia, the Nordic countries, with Norway, Sweden, and Finland, Canada, and the US. And this has been done in the framework of the IPFRA Insight process. And this is the first report, which is currently under scientific review here, which is called Sustainable Boreal Forest Management: Challenges and Opportunities for Climate Change Mitigation. And again, the first time all these countries, including political support, has been contributing here, and that was even requested by a ministerial meeting from this Circumboreal Working Group. So you see the importance here of working together very closely also with the political decision makers. So in order to move on with the idea here, one idea is to check, okay, what can now the forest, and particularly the Boreal forest, contribute? And one option is nature climate solutions. So the direct contributions to mitigation by creating negative emissions. And these negative emissions, land-based ones, and in combination with forest, for instance, can be can be done through a combination of bioenergy and carbon capture and storage on the one hand side, but on the other hand, also through afforestation. What is important that needs to be considered here is that all uptake that is not directly caused by human activities cannot be accounted under the UNFCCC rules. So whatever we do here in terms of afforestation and reforestation, it needs to be an additional effect to what is already happening from nature. Here is a little comparison of some technologies that can provide negative emissions. And we see here in the lower part, afforestation that can be quite effective in terms of reaching up to 4 gigatons CO2 sequestered and put negative per year. And the costs are relatively okay compared with all the other potentials and types of emission technologies here. Of course, we need to consider that there are different land requirements, different, for instance, water requirements, but that also, for instance, technologies like Beck's, bioenergy combined with carbon capture and storage, produce on the one hand side also energy for substitution from biomass. And afforestation per se does not produce any substitution energy. So here comparison is difficult. In the end, what counts is the negative emission potential. If we, for instance, compare this Beck's technology with afforestation, reforestation, and restoration under the SDGs and the nature contribution to people schemes, we see that, and we don't have to read that, but just look at the individual round dots here with little numbers in it. You can see it here in the outer circle and inner circle, that there are many more overlaps between afforestation, reforestation, and restoration with the SDGs, for instance, and the NCPs. Then on the other hand, where we look at Beck's only. So these multiple effects are also very important and can probably compensate for the substitutional energy that can be produced from a Beck's technology. Okay, but the big question is now, where can we do this afforestation and reforestation? And of course, this is an interesting question and the most important question, and what are the potentials? So let us look very quickly into what can be done in the Eurasia and circumboreal context. We first, of course, have to look what is generally globally possible in terms of the increment, what is needed in terms of NPP here. And we have to reduce this. For instance, we only would like to look into areas which provide an increment potential that is above 1 cubic meter per hectare per year. Otherwise, it wouldn't pay off. Then, of course, we have to subtract currently forested land, and that cannot be used because it's already used and there would be no additionality effect. And then we have to reduce all that from cropland and urban land, etc. And what in the end is left over is a rough potential for afforestation with a geographic identification here of 3 gigatons per year carbon. This is an important knowledge. However, also this we need to further play down and see if we can identify additional afforestation area. And one area particularly in the boreal forest arena and in the circumboreal context is probably abandoned arable land. And you might think that this is very difficult to control. We do it here and can observe this with satellite imagery, with remote sensing, but we also do studies like here where we looked at Russia and further 8 former Soviet Union countries, and you see all the red dots here. This is actually abandoned forest land. If we zoom into that, for instance, in Königsberg, you see that even large areas of certain territories are completely abandoned. And if we look around Moscow, it's surprising how much arable land is abandoned there. So there would be good potential for afforestation, particularly because we know that this has been a highly productive land for arable, for agriculture. And on the other hand, there is already infrastructure available. Okay, statistics also show that with our combined ground truthing and remote sensing methodologies, we can really say that there is more arable abandoned land available than we thought from the statistics. And the last point I want to make here, how about all the forest fires which are ongoing? Is maybe this area also available for huge afforestation activities? And we know that globally, under each of the different scenarios, the burned area is increasing. Of course, more increasing under the extreme RCP 8.5. But this in terms means that there is a huge climate impact on the forests, and we need to deal with that. So one way is to identify these areas, and we looked here into the Russian Federation with our FLAM model, and what are the accumulated and aggregated areas that have been burned. And we see, if we zoom into Krasnoyarsk Krai, for instance, that this is a substantive area, particularly that only areas are marked in red here that increase or exceed 100 hectares burned. So theoretically, and wouldn't there be other problems like accessibility, etc., this would be huge potential in order to do afforestation. And we compared here 3 different scenarios where we do nothing in terms of natural revegetation. Then there is an assisted and highly assisted scenario, and we can see that over the course of this century, we could achieve here an additional 1.2 gigatons if we help here with active afforestation on these burned areas. So these are first rough estimates, but in addition, of course, there is other ways that can be also considered here as available potentials. This is reforestation of areas designated for forest land, afforestation of abandoned land, assisted forest migration because it's getting warmer, so the forest is moving up north. We could accelerate that a bit, etc., and other uses. So we can come up to an additional 600 million tons carbon per year over this century. So these are our interests at the moment where we would like to look into, and how are we going to do that? We, for instance, are coordinating a large ESA, European Space Agency-based forest observation system project with many partners, for instance, from the region, particularly from Russia, where we have permanent sample plots where we do not only collect data, but also connect all the people and the scientists behind these sample plots together, which is extremely important. And this information is then, of course, published also in high-level journals, like here in Scientific Data. And another example is that this data that we collect then with this network can help us to also help understanding better if there are knowledge gaps. For instance, there was a shift in Russia from an old national forest inventory system to a new one, and suddenly there were quite different figures out there. And with this network, we could already submit a very interesting paper to Nature Scientific Report, which is under review there, where we can show that actually the biomass availability is 44% higher in Russia than the forest register showed. And you see that there is very huge participation, of course, from IIASA, and European institutions, but the massive contributors are, of course, the Russian institutions, where the 2020 latest figures from this national forest inventory have been used, and this is the first time that something is going to be published here with this new data. So what are some takeaway messages here? I will just pick a few. I would like to remind my first point I made with this information mapping and collection of scientific information. We do not have only the importance to look scientifically into the details, but that we also have to see particularly as a science to a policy institute, that there are sensitivities on political, but also other social and socio-economic levels that need to be considered. There's huge pressure on the forest, and we need to think how under this pressure we can still make the forest contribute to mitigate climate change. And another important thing is that always this integration of different methodologies is important. So permanent sample plots, for instance, on the ground, combined with top-down information from remote sensing, this is probably the way forward that we need to go, and co-benefits are extremely important. It does not help only to look at the direct economic output of some calculations, but we know, for instance, that if a methodology like afforestation provides also green jobs and supports the bioeconomy, not only directly, but also indirectly, this is equally important. And last not least, I would like to mention that we have no time to lose. We need to start looking into this and turning it into action. And with that, I would like to thank you very much.
Thank you very much, Dr. Kraxner, for a very impressive presentation. Who has questions to the speaker? Okay, I do. There is a proposal, a plan, incentives, if you wish, to probably to deploy a smear station of this Finnish international system presented in the first talk of Dr. Beck in Russia. If this is the case, and this is under the discussion nowadays, if this is the case, where do you think would be the best place for such comprehensive observatory as far as forests are concerned and other things?
Very good question, because probably not only forest belongings can be considered here, but definitely if this is you mean a center of research being established there?
No, not really. This is like a flagship station of SMER.
Well,
like, for instance, is deployed now in Estonia.
Mm-hmm. Mm-hmm. Well, I think, yeah, again, the question is not easy to answer. Considerations would be, of course, a forest density. I think it cannot be at the brink of forests. It should be probably in rather unmanaged areas in order to get insight that is looking at unmanaged versus managed forest. So these are considerations I would bring in here. But this is probably also a question to Professor Beck here, where such a station would be ideally placed. It's a very good question, and I never thought about that, but I think it would be interesting to cover a huge territory of forest that is under change. And I think that there are some other places that cover well the managed area of forests, and Russia would be an optimal territory in order to look into a vast area of unmanaged forest.
There is always one thing that should be taken into account, is that, let's say, Eastern Siberia looks as an ideal location, but there is no infrastructure there.
Yeah.
You should have electricity, you should have roads, you should be capable to come by airplane or even helicopter, all that. Okay, so other questions, please, to the speaker.
If I may comment, and I have also a question to Florian. This was a good question on the station location and distribution, and I think there's no right or wrong answers. What Markku Kulmala said in his Nature paper was that approximately in 1,000 kilometer from a distance apart from them each other would be kind of one way of looking at it, but of course it would be needed to be looked at from scientific perspective. So what is meaningful? What is the information gap that we are wanting to address here? And toward this end, I think that the one solution is that there can be a hierarchical station network, not only consisting this kind of master stations or flagship stations, but also including some that are not measuring everything, but are measuring enough basic variables that can then be used for upscaling and modeling the effects. So there is enough food for models to be then used in interpolating and upscaling the results. That would be kind of maybe an intermediate solution from the station perspective.
Since we're speaking here about the big data, apparently the number of parameters measured is important. So, for instance, as I remember, your flagship observatory in Hautala measures more than thousands parameters.
Yes.
So what will be the number of parameters to measure for the beginning, you think?
Currently,
if it is 100 parameters,
yeah.
Is it valid or not? Or
Well, I would say that 1,000 is definitely way too much for measuring in many stations. That's the flagship station property that you can do in these cases, but I would probably go something like close to 100 parameters would be even sufficient for most of the models that can be then deriving the basic characteristics of the ecosystem, and then when it's done constantly so that it is repeated in a regular intervals or measured constantly, then that would be, of course, providing good grounds on analyzing also the dynamics of features and processes.
thank you very much. Please convey my best regards to Markku Kulmala.
I will, for sure.
So we come to the last speaker before my observations of our session. This is Professor Mizui Ohashi, who currently works as a full professor in the University of Hyogo, Japan. She's a specialist of forest ecology in biochemistry. So in our session, we have a big deal of forest presentations, what is typical for IIASA, by the way. And the roots goes to number of very famous and important scientists who used to work in IIASA. She's a special, Mizui Ohashi is a specialist in below ground biological processes of carbon dynamics and forest ecosystem. In her career, Dr. Ohashi used to work in Finland in 2003 as a postdoc scientist in Finnish Forest Research Institute in Joensuu, Finland. In Finland, she joined an international project. Do wood ants play an important role in carbon and nutrient dynamics in boreal managed forests? In 2007, Mizui got associate professor position in School of Human Science and Environment, University of Huago, and then she got full professor position there in 2016. She started several new projects that includes the role of wood roots on soil carbon dynamics and molecular composition of dissolved organic carbon in the forest in Finland and Japan. Now she wishes to connect her studies in different types of forests in Japan, Malaysia, and Finland. Please, Dr. Ohashi, the floor is yours.
Can you listen me and see
Yes,
my?
we hear you well.
Yeah, thank you for introducing me. My name is Mise Ohashi, working in University of Hyogo. Thank you for inviting me to this session. Today I talk about my field study in Finland mainly. I am field researcher and my study site locates various countries including Finland, Thailand, Malaysia, and Japan. My talk is much more local than the other talks, so I hope my talk suits to your interests. So first, I want to explain why Finland. Finland is one of the countries that stocks huge amount of carbon in soil. You can see in this figure that soil carbon stock is very high in Boreal region, and Finland has darker red color, suggesting high carbon storage country. In Finland, carbon stock is also increasing in forest by continuous forest protection and management. This means forest management is a key human activity affecting the carbon stock in Finland. Finland has a flat geophysical feature, and this contributes to keep the water resources in the land and keeping low amount of carbon outflow from the land to surrounding ocean. Climate in Finland is also suitable for keeping the carbon in soil because of low mean temperature and precipitation. So this Finnish climate inhabits organic matter decomposition in soil. So Finland is the country that contributes carbon isolation from atmosphere because of its climate, geophysical feature, and human activities. This means Finland could be a model country for understanding the mechanisms of the carbon storage in boreal ecosystems and for predicting its future changes. So today I focus on two questions and introduce my research activities in Finland relating to these two questions. First one is how carbon cycling in boreal forests are different from those of others. So here I introduce my research about the role of ants in carbon dynamics in boreal managed forests in Finland. This figure shows carbon cycling in a forest ecosystem. Please look at the red circle, the carbon flux from soil surface to atmosphere. The CO2 flux from soil surface is called soil respiration. Soil respiration is the second largest flux in carbon cycling in a forest. All living or soil organisms, roots, soil animals, and microbes contribute to soil respiration. Soil microbes and roots would be the main source of CO2. Soil animals could increase CO2 emission directly and indirectly. Then, one of the most common soil animals in boreal forests, especially in Finland, is the redwood ant. This animal is so-called Formica lufa group, consists from several species of genus Formica. Redwood ants make a big mound in forests like the one in the photo. The size of mounds could be 1.5 meter height and 2 meter diameter. And ant mounds are made from little resin honeydew collected by ants. This means ant mounds accumulate a lot of carbon and minerals compared to surrounding forest floor. It is also known that temperature and moisture in mounds are different from those in soil because of the ant activity. The special mound environment may affect the decomposition of mound material and cause different carbon and mineral dynamics. This figure explains the hypothesis of carbon flow via ant mounds. So carbon come into mounds by as little resin honeydew insects collected by ants. Then they decompose at the ant mounds, and CO2 and DOC emission occur from the ant mounds. This could be different from the CO2 emission and DOC leaching from the forest floor in Finnish forest. So the aim of this study is we established two aims in this study. One is to develop a method to measure CO2 flux from ant mounds, and the other is to estimate the impact of mounds on total soil respiration. We established our study sites in Kori National Park in eastern Finland. 4 different aged stands were selected to conduct experiments. In order to measure carbon flux from ant mounds, we developed special chamber like this figure. Basic structure of the chamber is a modified closed dynamic system. Then we made a big chamber to avoid disturbance of mounds. Light and transparent material like vinyl sheet were used to keep natural environmental conditions and to finish the measurement as soon as possible. We then avoid to disturb ant behavior. This is a photo of CO2 flux measurement from ant mound using that special chamber. Environmental factors such as temperature and moisture content was also measured continuously using sensors in ant mound and the surrounding forest floor. So this is a part of the result of this experiment. We found that CO2 flux from ant mound was higher than surrounding soil respiration, and the temperature and moisture content in ant mound were also higher than those in surrounding soil. And the difference between mound and soil increased in growing season because of active ant behaviors. There was no relationship in soil moisture. No relationship was observed between CO2 flux and moisture content, but we found exponential relationship with temperature in both of mound and forest floor. We found that CO2 flux from mounds increased with stand age. However, the contribution of mound CO2 flux to total soil respiration was less than 1%, very small. We also simulated the changes in mound CO2 flux and soil respiration under global warming scenarios. Our results suggest that the impact on ant mound on total CO2 flux will not change much under global warming conditions. Now I introduce another study about the effect of natural disturbance on carbon dynamics in Finnish boreal forest. The title could be Changes in the Quality of Dissolved Organic Matter in Soil Water with Time Since Last Fire in Boreal Forest. It is known that most of non-living organic carbon are mineralized by microbial decomposition and go away by soil respiration. But part of the decomposed carbon dissolved into soil water and flow away from the ecosystem. And little is known about the role of DOC in carbon cycling. However, DOC play an important role in retention and transport of nutrients and metals. Wildfire is an important trigger of the start of forest succession in boreal forest. Fire seriously affects carbon stocks and cycles and may also change the quality of dissolved organic carbon. Therefore, the aim of this study is to clarify how the quality of DOC changes with time since last fire in boreal forest soil. This study site locates in Scott Pine Forest in Finnish Lapland area. We collected soil water from 2 different types of forests, which have 6 and 156 years old, respectively. Then we analyzed the collected soil water using Fourier transform ion cyclotron resonance mass spectrometry. This technique is used for finding the molecular formula of each molecule in DOC in water samples. The technique, this machine itself does not give the molecular formula, but we can get very accurate M-per-Z value of mass peaks from this machine, and this allows us to predict a molecular formula of each molecule in the sample. Using the number of oxygen, carbon, and hydrogen atoms in the estimated formula, we can make Van Cleveland diagram in order to divide the DOC molecules into 7 biomolecular classes: lipids, protein, amino sugar or carbohydrates, lignin, tannin, unsaturated hydrocarbon, and condensed aromatic structure derived from the black carbon made by the fire. And this figure shows the main result of this study. Our results showed lignin-like molecule and dissolved black carbon molecule are higher in less than 3 bond forest. The peak intensity weighted average molecular weight of molecular species that was not shared between the less than 3 bonds and long unbound sites were different in amino sugar carbohydrate and tannin-like molecule and dissolved black carbon. This means molecular composition of these classes changed by fire burning. So this is the summary of these 2 studies. My answer to the first question is that forest living organisms such as ants contribute to produce a unique carbon cycling in boreal forests. And the answer to the second question is that carbon molecule composition can change by fire. That is a trigger of forest succession in boreal region. Finally, in the end, I want to introduce my ongoing project in Japan. Now we have network study of woody root dynamics called RootNet. So there is a mystery of root phenology in forests. We don't know when roots are born and when they die. And we don't know how roots are born and how they die because they grow in soil and we cannot see them. So it is easy to understand life stages of leaves, branches, stems, above ground part, but it is very difficult to know life stages of pine roots. We don't know whether they have only 1 peak growing during a year or 2 peak growing during a year. In order to answer these questions, to clarify these questions, we are trying to use scanner method. In this scanner method, we collect soil images in field by setting a scanner in a transparent box. Root behavior in the soil is monitored directly. Then root dynamics is detected by repeating the image collection. We developed already the manual for extracting root dynamics from a series of scanner images. Then we tried to determine the variation of root phenology in different regions in Japan now. We established nearly 15 sites to compare fine root phenology in different regions in Japan. Then we established a RootNet scientific network to exchange our information and knowledge and discuss our future challenges. Now more than 50 people, including scientists and students, belonging to join this RootNet network. So thank you for your attention.
Thank you very much, Dr. Huishi, Ohashi, and your paper is open for questions. Are there any questions? No, so no immediate discussion because everything was so clearly reported. Thank you once again. And now, Sergey, I address Sergey Sizov. Can you start my presentation? I would like to share with you some points concerning big data and possible application of this. It is Arctic studies. Next slide, please. So first, the notion of big data firstly appeared quite long ago. It was quite long, not in geological terms, but in our everyday terms. So the author of the big data term is Clifford Lynch, editor of Nature Journal. On September 3rd, 2008, he issued a special volume of the journal on the topic, how can technology that open up high possibilities to work with big data influence the future of science? That was followed by explosive growth of data volume and variety. Leap from the amount of initial data to the quality of recognized knowledge was a characteristic feature of this new movement. Next slide, please. Little by little, but very fast at the same time, in the 10th of the 21st century, revolution in data science appeared. The transition of the quality of the accumulated information to into the quality of the problem solution is called big data phenomenon. Today, it is one of the most discussed concepts in the IT science and industry. Data now are no longer seen as a statistic value. They have become the material for creating new economic values. In our century, in the ongoing century, software technologies like MapReduce of Google and Hadoop of Yahoo have appeared. For them, the original information is no longer needs to be lined up in neat database tables. In result, the big data processing technologies emerge without the previous rigid hierarchy and homogeneity. Next slide, please. And a very important thing happened. In the big data world, the search of causality will have to be abandoned in favor of the search for correlations. In other words, the data processing, in order to answer the question why, became replaced by the search of the answer to the question what is it. This change in the research paradigm shortens the transition to prediction. Actually, this is the step that never happened before. Maybe it happened only at the time when mathematical modeling appeared. And at that time, question why that happens started to be the most important. With the big data, still it is important, but this is not the mainstream of what is going on. The mainstream is to look for the correlations. For instance, what is more important in coronavirus studies? To understand who was the first patient of this pandemic and how this problem came to us, or to understand in details what is it. For instance, if we would know the correlations of the coronavirus with the absence of the vitamin C, if we would, we can say that people who eat many oranges and mandarins and drink vitamin C are better placed towards this pandemic. But we don't know that, unfortunately. Next slide, please. Definition of big data is horizontal scaling is dividing the system into smaller structural components and spacing them into separate physical machines, or increasing the number of services, nodes, and processors that simultaneously perform the same function. Big data is structured and unstructured. The second point is the most important. We should be capable to store the big data in the way different types of data are there. Texts, movies, remote sensing information, figures, digits, all that should be together. So big data is structured and unstructured data of huge volumes and significant diversity, efficiently processed by horizontally scalable software, alternative to traditional DBMS. This is exactly what was said when I commented the previous slide. This is a Hadoop. Next slide, please. This is just the list of mathematical methods to extract knowledge from the big data. This is like a coin. Big data, this is the data and principally new approach, mathematical approach to process this data. They are listed on this slide. And this is actually what in IIASA is called systems analysis. So we can make a conclusion here saying that in the same way how mathematical modeling became systems analysis for the studies that plan to answer the question why, and the mathematical models help to answer this question. In the same way, this list of methods helps to answer the question, what is it in details? And this is modern systems analysis, at least how IIASA understands that. Next slide. Classical example of big data is the internet. You see impressive figures of how much is, how big is this world of the data, of the big data. Next slide, please. However, not all the data is big. It should not be mixed between good data and bad data. Big data and not big data, this is different. Very important, very good, very precise data can be not big data. For instance, I work in earth sciences, and in our sciences, we know just 5 types of data that satisfy the conditions of the big data. This is meteorological data, Earth remote sensing data, data ecological superstation SMER2 information, oil and gas seismic surveys, seismograms monitoring. And the upcoming big data. This is Arctic comprehensive information, and this is a great source of big data. Since our time is over, I will stop here and just will make an appeal to our session participants to discuss how SMER data can be affiliated with the big data postulates. Recently, I gave a paper on this matter to one of the Russian journals translated into English called The Physics of the Earth. Thank you very much. And I think we had a very nice session. Let's have maybe short discussion, 5 minutes, if anyone would like to comment something particular. No speakers in the discussion, and we are late at the same time. So thank you very much to all of you. I think that was a wonderful session, wonderful speakers, and the moderator enjoyed that very much, and hope this will be well reported in the IIASA information boards. Thank you to the organizers, and our session is over. Bye-bye. Have a nice day.
Thank you. Thank you very much.
Thank you very much.
Bye-bye.
Oh. Sergey, are you still on the on Zoom? I'm addressing Sergey Sizov.
Yes, Alexey Germanovich. It seems we might be still live.
Good. Good. So I'm interested to take part to listen the next session.
Sure.
So I will be here with you.
Sure. Very much welcome.
Now Igor Sheremet will be chair, right?
Correct. Mm-hmm.
Okay.
May I proceed with the poster session?
Yes, please.
Okay, so ladies and gentlemen, esteemed colleagues and friends of IIASA, welcome again from my side. For those of you who joined for these sessions only today, I'm Viktor Bruckmann, representing the Austrian Organizing Institution, which is the Austrian IIASA Committee. I do have the pleasure to moderate the poster Blitz sessions during this conference, which are scheduled in between the scientific and discussion sessions of each day. Let me do, before we start, some organizational housekeeping at first. Poster sessions are divided into 2 blocks. The first block, which we are starting right now, provides a brief introduction on each poster to the entire audience. Each presenter has no more than 2 minutes to introduce the topic, and I will carefully observing the time here, just as a side note. After this block, we will open a separate Zoom session during the coffee break of the event, the conference, where you can then get in touch with poster presenters individually for further discussions and in-depth questions and so on. In addition, I would like to point out that all posters will be also available for further discussion and interaction at the IIASA Connect platform, even beyond the duration of this conference. So let us now straight jump into the poster presentations, and I will introduce the first speaker. This is Veronika Ginsberg from the Institute of Global Climate and Ecology And she will introduce her poster on black carbon in Russian Arctic, main emission sources. Veronica, the floor is yours.
Thank you very much for the presentation. Dear colleagues, can you see my screen?
Yes.
Okay. So I would like just in this very short time to present the main results and ideas of our study on black carbon in Russian Arctic, main emission source. It was made under the support of the Russian Foundation of Basic Research project. Unfortunately, black carbon is not included in official inventories in Russia. So there are quite a lot of different researches and estimations of its emissions. But we consider that one full inventory should be made, and we as an institute who is responsible for greenhouse gases emissions in Russia are also taking this research on black carbon emissions in Russia from different type of source categories. So in our poster, which you can see in this IIASA account for this conference, you can see in more detailed results, but I would like just to stress the attention that for example, if for all Russian territory we have main emissions of black carbon from energy production, from residential combustion, from industry, stationary sources, but in Arctic region, especially for oil and gas regions, mining oil and gas regions, main emission sources, stationary emission sources of black carbon is flaring. And you can see on this chart in the bottom, left bottom, that it could be up to 100% for some regions. And if you look to mobile sources, then you can see them for the whole Russia, road transport is the main source, but for Arctic region, this is off-road transport and marine transport emissions. And this slide represents the total emissions of black carbon in Russia, according to our estimations. This is only for anthropogenic sources. We have also inventory for forest firing, but it is outside of this presentation. And you can see that for anthropogenic sources, these emissions are not very much varying from one year to another year. And according to our estimations, it's about up to 60,000 tons per year, which is much less than for many other inventories made by other authors, and particularly made by IIASA. So I think that this
Veronica, please conclude.
Yes, this is a conclusion that this is an open field which needs more detailed estimations and more detailed investigations for the Russia territory. Thank you very much for your attention.
Thank you, Veronica. The next poster will be presented by Mohamed Humran from Sana University, the Union of Arab Academics. And he will talk about the role of non-governmental organizations, NGOs, in managing environmental risks in Yemen. So we are jumping from the Boreal region to Yemen. Mohamed, the floor is yours.
Good afternoon, everyone. Yes. Did you see my slide?
Not yet.
Okay. So yes, my article talk about now it's clear. You can
Yes.
see, right? the role of non-government organization on managing environment risk in Yemen. Actually, we have really risk affected in our environment, such as waste disposal. So the house waste disposal affected, especially in Sana'a city. There is a collective camp in the north of Sana'a, and we find the wind and the garbage affected in the people, environment. There are many people affected and found many difficulty to live there. So as we are working in the Union of Academic, we decided to build mini factory that we could manage risk in Sana'a city and build recycling waste disposal. So we have study that I can give you the abstracts. It's here. When I traveled to China, we have international conference in China, and we visited one of the important company. It's called Blue Green. So we decided to do the same factory in Yemen, and we can serve the environment. Actually, it's really a risk because the people increased. We found that if people produce 1 kilogram per day, it will be most period we will get 60,000 tons of garbage. So it's really a risk and affected an environment. We need to find how can connect between modern technology and building many recycling plan so that we can produce electricity, and we support young inventors, because we also interested in innovation and research in Sana'a city. So the factory
Please
will
conclude.
help. Okay. Help more than 1,000, and the cost more $200 million. Thank you so much.
Thank you very much, Mohamed. Our next speaker will be Peter Lomander. He is from the Swedish company Optimal Solutions, where he is the founder and president. He will talk about forest fire expansion under global warming conditions, multivariate estimation, function properties, and predictions for 29 countries. Peter, the floor is yours.
Thank you. Please remove the presentation.
Mohamed, please.
Yes.
Thank
Thank you.
you.
Okay. Now good?
Yes.
Dear colleagues, it's a pleasure for me to be here. I'm Peter Lomander from Sweden. I will talk to you about forest fire expansion under global warming conditions, multivariate estimation, function properties, and predictions for 29 countries. Problem: forest fires create large economical and environmental problems in many countries. Question: how will forest fires be affected by global warming in different countries? Solution: a new prediction model has been developed. We move directly to the results, and you can read everything about the background to this particular model in the journal that I will show you on the next slide. But the results are the following. Relative burned area, B, in percent in a country is determined from the following equation. T represents the average temperature, P is the size of the population, and A is the total forest area in the country. And as you see in the function down to the left, you see that the P values are very, very low. So the precision in this function is very high. And to the right, you see table 6 with predictions of average fire areas as functions of the level of change in the average temperature in the different countries. And there you can see, if you can look at different countries, and you can say that DT is 0 represents the present situation, and DT is +1 is what happens if the temperature increases by 1 degree. Main conclusions. The estimated model predicts that global warming will increase the areas of forest fires. The future developments of expected forest fire areas in the 29 countries have been predicted for alternative levels of global warming. And here you can download the article that describes this exactly, and you can also find misprints and related research and contact information. And I really want you to look at the related research link, because there you can find many other articles with very much related contents on global warming and such effects. Thank you very much.
Thank you very much, Peter. And our last speaker in this poster blitz session will be Olga Maximova, and she will introduce her topic, selection of a climatic model for forecasting the surface air temperature in the continental part of the Arctic region. She's affiliated with the Institute of Global Climate and Ecology and one of the organizing institutions of this conference, the National University of Science and Technology in Moscow. Olga, the floor is yours. You're still muted.
Dear colleagues, the aim of our study is to test the approaches to assessing the reproducibility of regional characteristics of surface air temperature using global climatic models. The Arctic region of Russia was selected for testing, and we solved two main tasks. The first task is to select the most accurate model, climatic model, and the second is to construct a multi-model which can serve as a basis for forecasting in this region. You can see three approaches, which include a dynamic matrix analysis and numerical matrix analysis. And I can say that each approach has advantages and disadvantages, but using all three approaches makes a complete comparison and removes the disadvantages. The final result you can see in this slide is the selection of the most accurate models that should good result in all three approaches. These models are Britain model, France model, and Norway model. But model Britain is the most accurate. We built a multi-model. You can see a multi-model in the second picture on the right of the slide. And you can see a picture for Britain model in the first picture. And you see that our multi-model is more accurate than each of them. It is all, I think. Thank you for your attention. Thank you.
Thank you very much, Olga. Thank you indeed. Thank you to all poster presenters of today's poster blitz session. Now it's time for the audience to switch over to the individual discussions by connecting to a separate meeting. The link will be made available in the chat within this session for all those who are on the panel, and for the audience, the link will be provided by IIASA's website where you stream the entire event. Make sure to reload IIASA's page, then the message will appear if you can't see it right now. Presenters of tomorrow's poster session, and this adds even to the diversity we have been experiencing so far, will be also joining this individual Meet Poster Presenters meeting. So you may also discuss with, and I will just briefly mention so that you know what you can expect, from Purnima Kumar about sustainable alternative futures for urbanization in India. You can discuss with Itumeleng Selebalo on environmental impacts of gold mining in South Africa. And you can discuss with Monique Dingoko on the entrepreneurial ecosystem in Philippine social enterprises. I would like to remind all of you that we have also a Best Poster Award, which is very attractive as it comes with a full travel support for the next regional conference. And as such, I would like to ask you to not forget to vote for your favorite poster. And this can be done via IIASA Connect. The link will be provided. Of course, this is possible for the entire audience, for poster presenters of yesterday, today, and of course, tomorrow. That's it from my side for today. Thank you very much for all the poster presenters. Thank you for the audience for your attention. And I wish you an inspiring afternoon and a great day tomorrow at the continuation of this conference. Thank you very much. To all poster presenters, Mohammed, Olga, please kindly join the poster individual discussion session. You can find the link for this session in the chat function.
Hi, good afternoon, everyone. Or good morning, I should say, for some people.
Good morning.
Or good evening, maybe, for some others too.
Jan, would there be one more delay, or as you promised, 15 minutes, we shall begin?
Yeah, no, in 15 minutes we will begin. They're just finishing off the poster session in a different room, but that's fine. We can start at 15:15.
Thank you. So you shall tell me when I shall...
Yes, yep.
speak.
I'll tell you when we're live.
Yes, thank you.
So Igor, we're ready.
Yes, I'm ready, Jan. Thank you. May I begin?
Yes, please.
Thank you. So, hello, dear colleagues. Hello, dear all who are ready to watch our panel via Zoom and YouTube. As it is pre-planned by the program of the conference Systems Analysis in Eurasia, we begin our panel discussion advancing the frontiers of systems analysis and mathematical aspects of systems analysis. I am Professor Igor Sheremet, and I shall be the moderator of our panel. I am Director for Science of Russian Foundation for Basic Research and Vice Chair of the Committee for Systems Analysis of Russian Academy of Sciences, being the IIASA National Member Organization. Let me begin from introducing our panel speakers. Professor Fred Roberts is a distinguished professor of mathematics at Rutgers University, the USA, and Emeritus Director of DMACS, the Center for Discrete Mathematics and Theoretical Computer Science, which have directed for 16 years. Also, he is currently Director of the Command Control and Interoperability Center for Advanced Data Analysis, the University Center of Excellence of the US Department of Homeland Security. He is author of more than 200 scientific articles and editor of some 30 books, The Mathematics of Planet Earth, published at 2019 among them. His works have been translated into Russian and Chinese and deal with such varied topics as discrete mathematics, decision-making, sustainability, global environmental change, mathematical psychology, epidemiology, disasters, and pandemics. He is fellow of the American Mathematical Society. He received the US National Science Foundation Award, Award of the Association of Computer Machinery, ACM, and was awarded the title Doctor Honoris Causa by the University of Finn. Fred is a good friend of mine. We are co-chairs of the CODATA task group, Advanced Mathematical Tools for Data-Driven Applied Systems Analysis, and also co-editors of the book Resilience in the Digital Age, published some 2 months ago by Springer in the well-known lecture notes in computer science series. Professor Abraham Neyman is professor of mathematics at Hebrew University of Jerusalem, Israel. He is one of the world-famous scholars in the area of game theory. He has served as the game theory editor for the Journal Mathematics of Operations Research, on the editorial board for Games and Economic Behavior, and the International Journal of Game Theory. He served also as the president of the Israeli chapter of the Game Theory Society. Professor Neyman also held positions and have been a visiting scholar at such world-leading institutions as Stanford University, Harvard Business School, Cornell University, the University of California at Berkeley, Stony Brook University of New York, and the Ohio State University. In 2020, he became an elected member of the Academia Europaea, the European Academy of Sciences. Professor Ahti Salo is professor of systems analysis at Aalto University, Finland. He has worked in the area of decision analytic methods and the application to resource allocation, efficiency analysis, innovation and risk management, foresight and forecasting. He is author of over 180 scientific papers and have received several awards for his research from the Institute for Operations Research and the Management Sciences Informs. Professor Salo has been the president of the Finnish Operations Research Society for 2 biennial terms. He has been visiting professor at the London Business School, the University of Vienna, and the University Paris-Dauphine. He is a member of the Government Foresight Group appointed by the Prime Minister of Finland, and also he was a member of the science panel appointed by the Prime Minister's office for obtaining scientific support for the management of the COVID-19 pandemic. Dr. Lena Ryonsky is the program director of the Advanced Systems Analysis program and also acting program director of the Evolution and Ecology program at IIASA. She is also a research scholar at the Optimal Control Department at the Lomonosov Moscow State University. Her scientific interests are in the areas of optimization, decision support sciences, and mathematical modeling of complex socio-environmental systems. Dr. Ryonsky is leading a team of some 40 high-skilled scientists at IIASA who focus on the latest development in applied mathematics and modeling towards advancing systems analysis methodologies and applications. So, as you may see, we have the very distinguished and high-level experts at our panel. And now we may move to its main topic, which is advancing the frontiers of systems analysis and mathematical aspects of systems analysis. Before I shall give a word to the first speaker, let me make a few remarks concerning the main content and objectives of our panel. Let me say that systems analysis is understood so far as a most general and widely applied methodology of consideration and solution of multiple complicated problems. Assessment of systems resource consumption, vulnerability, and resilience to destructive impacts. Systems optimization and design given external and internal constraints and objectives. Systems reverse engineering given the multiple measurements and signatures available as big data sets. Strategic and situational planning and scheduling their behavior in the highly volatile and often hostile environments. Their cooperation and conflicts, and so on. This methodology regards large-scale technological, economical, social, ecological, biological, socio-technological, and any other kinds of systems. This methodology far and wide presumes consideration of systems of any nature from some general points of view and application of some basic mathematical tools, toolkits, and frameworks, providing adequate and constructive system description and handling their mathematical images. In this quality, systems analysis is often named science of sciences, referring to its integrating, joining role in systems' formal representation and modeling. And namely, in this quality, systems analysis and high-skilled system analysts and scholars have the greatest value for decision makers from various national, transnational, and corporate policy and economy staffs. So let us make an attempt to consider the main issues associated with modern systems analysis, beginning from its mathematical background, then application of available mathematical tools to multiple problems, up to transfer results of this application to high-level decision makers and providing the right advertising. And by this, we shall try to understand how the aforementioned mathematical background of modern systems analysis would advance its frontiers and make its application more and more useful. Keeping in mind these introductory remarks, let us move to our discussion. So with great pleasure, I give a word to Professor Fred Roberts.
Good morning, everybody. Can everybody see my screen?
Yes, we see.
Very good. So first of all, thank you, my friend Igor, for including me. It's an honor to be here and a pleasure, and it's been an honor and a pleasure to collaborate with you. I hope that will continue for a long time. So let me go back. Let's see, my slides are not moving at the moment. Okay, there we go. So I'm going to talk about the tools of systems analysis and new mathematically based tools that are related to decision support applications. And what I'd like to do is stress some of the applications and challenges that we face in systems analysis, and mention the types of new mathematically based tools that are relevant to those challenges. So, and my slides are having trouble moving along here. I'm not sure why. There we go. Okay, so we have remarkable new mathematically based tools, and those tools are really relevant to the problems of the planet that we all face, in particular the problems that have been highlighted in this past very difficult year. A lot of the work is underscored by the dramatic amount of data that's available and the amazing tools that can be used to use those data to make better decisions and influence policy. And that's what I'd like to talk about. So for some reason, my slides, there we go, are not moving very well. Okay, so the first theme I'd like to touch upon has to do with fusing lots of data to make better decisions. And here, let me first mention some applications of modeling and simulation. Now, those are not new tools, but they have new ways of applying them. So I want to emphasize some of the urban issues that modeling and simulation might be relevant to. So as we know, the world's population is moving toward living in big mega cities. At the same time, climate change is having a serious impact on urban areas with more severe hurricanes and droughts and storms and heat waves and so on. About a decade ago, we had a superstorm that we called Sandy in New York City. And that storm flooded the subway tunnels. Already at that time, mathematical models developed by a professor at Columbia University were able to predict which of those tunnels would be flooded, and they were very accurate. And now the question becomes, and this is something that the New York City Climate Change Initiative is concerned with, is as we plan ahead for sea level rise in urban areas, can you predict using models and simulation which power plants might have to be moved because they're on low-lying areas, and which train tracks might have to be raised because they might be flooded and so on? So those are some of the new challenges that we face with modeling and simulation. Now, for a second application, I'd like to talk about the health of ecosystems and the concept of biodiversity. With biodiversity, we want to be able to measure how well we're doing in terms of the variability of the plants and animals and our ecosystems in general. And in recent years, tools like artificial intelligence and machine learning have come to be very helpful in measuring biodiversity, and in particular, helping to identify species. So we have, as an example, a project that's called Snapshot Serengeti. With this project, as well as many others, there are camera traps set up around the world in remote areas mostly. They're motion sensor cameras. They collect millions of images of individual animals. And there is now an app that has been launched by Snapshot Serengeti that uses deep convolutional neural networks and is able to identify whether what you saw was a lion or a leopard or a jaguar or whatever. Enabling us to do that extremely accuracy, almost 94% accuracy. And that is an aid to identifying the size and health of populations. Now, the next step, which is the harder step, is to identify an individual animal, because you might have counted that lion multiple times and you actually would like to know whether it's the same lion you saw or a different one. That is the next challenge for artificial intelligence and biodiversity. So let me mention next a supply chain challenge as another challenge that has to do with getting lots of information and fusing it. So the recent blockage of the Suez Canal by a grounded container ship has had an amazing and widespread effect on the world supply chain. The supply of oil, the price of oil, the availability of food, the availability of microchips to make cars, which have caused some car makers to shut down. Empty containers being stuck at some ports and not enough containers at others. Here, we're beginning to see multi-agent simulation as being helpful to model supply chain operations, and in particular, to help predict the impacts of this kind of disruption. And in fact, the complex disruptions that we're likely to continue to see to the world's transportation system. And at the same time, such simulations are useful by making use of multiple intelligent autonomous agents to help us understand what kind of mitigation strategies might impact the disruption and reduce its impact. So another comment about climate change and vessel traffic has to do with the Arctic and the increased use of the Arctic Passage for vessels. And by the way, considerable possibility when there are choke points such as the Suez Canal would be Arctic passageways. Coming along with this are threats and challenges of oil spills. And we need to plan ahead for the possibility of oil spills in the Arctic. It's not the same as in many other parts of the world, because here we have long transit times, lack of infrastructure, remote locations, few roads, difficulty with the weather, and so on. Lots and lots of data exists about kinds of equipment that's relevant, transportation routes, communication methods, and so on. How do you decide how to allocate resources in planning for an oil spill response under uncertainty and at the same time having constraints in your budget? So what oil spill response equipment should be forward located in advance? What should be prepared to surge forward if there is an issue? How does the season affect things? What happens in the near term versus the long term? For all those questions, we're seeing the beginning of tools of stochastic programming being used to answer questions of those sort. So let me turn to the next general theme, which is sequential diagnosis. And here we have a variety of tests available. You choose the next test on the basis of results of earlier ones. Typically in medicine, for instance, you find that some of your blood result numbers are not so good, so you have scheduled for another test based on that, and so on. Here, tools like optimization of decision trees have turning out to be helpful. One method I would mention has to do, it actually arose with inspection processes for containers at ports of entry. But similar applications arise in education testing and testing for disease and so on. Here, the problem is that the number of possibilities, the number of possible orders in which to do tests is just very large. And we like to represent the problem as a problem involving binary decision trees. And the question is how to find the optimal binary decision tree in some sense. And these decision trees explode in number. So even if you have 5 possible tests and you can do them in different orders, you can have over 260 million possible decision trees, binary decision trees, and you need better search algorithms to move from one binary decision tree to a better one. Sequential diagnosis is also coming to be used in testing for COVID. Here are large-scale linear programming tools like sensor tree are useful, and we try to optimally select from the available tests the best one according to price, availability, efficiency, and accuracy, depending on the roles of the person you want to test. Do they have to go to work right away? What kind of work environment do they work in, et cetera, et cetera. So let me turn next to the general principle of data-driven decision science. So what's new about decision science that hasn't existed for many years? The difference is data science and the availability of being able to, of a vast array of alternative solutions that we can compare. And here we have the tools of algorithmic decision theory, very relevant. And with algorithmic decision theory, we exploit algorithmic methods to improve the performance of decision makers. So I mentioned, for example, the Ebola outbreak in West Africa of 7 years ago. It should have reminded us that we were ill prepared for a worldwide disease epidemic. But unfortunately, I don't think we were all that well prepared when COVID hit. I will say that the successful fight to contain the Ebola outbreak was heavily influenced by algorithmic decision theory, which allowed us to accurately predict disease spread and how to contain the disease, and allowed the decision makers to understand things like how many beds and lab tests they would need and where and when to deploy them. And I think during COVID, the worldwide collaboration of modeling and simulation, making use of a literally tsunami of shared data, have helped decision makers save lives. So I'm still having trouble with my screen. Here we go. So let me turn next to another point of decision science. And that has to do with supply chains. So artificial intelligence and machine learning have enabled us to minimize inventories because we have extremely accurate knowledge of demand for goods or components. And that allowed us to get just-in-time delivery of goods. Very efficient until something goes wrong like COVID. And then we have shortages because we didn't plan ahead for surplus and stockpiles. And here are tools of algorithmic decision theory I think are relevant as we go forward and rethink the role of AI and machine learning in supply chain. So here we have modified tools of machine learning probably will help us identify alternative sources and changing priorities in a fast way. Maybe data-driven decision-making will help us support decisions about how large stockpiles should be, where they should be located in case of a natural disaster of one sort or another. So last theme, and I'll end very quickly, is information sharing. That is enable us, hopefully, for all kinds of organizations and individuals to work together while protecting their private information. Could be useful in applications where we have multinational partnerships to work on sustainable development, where we share information about energy use in the private sector, maintaining the private information that individuals or organizations or countries have while allowing them to collaborate. And here I just mentioned two tools that are under development. One is called secure multi-party computation, which allows multiple parties to compute something jointly, and blockchain that provides a decentralized record-keeping system that allows them to transact safely without requiring a middleman. Next tool I want to mention has to do with a trust mark. That's a digitally signed assertion that shared between parties that allow you to trust someone. And that's important in disaster situations where we have lots of data as to damage and physical needs and so on. What can you trust about the data and the person who's giving it to you? And sharing information about water quality, air quality, flood risk, and so on. And the final thing I'd like to mention has to do with information sharing and identity and access management. Proving who you are and what kind of skills you have is critical in disaster situations and in others. So do you have the authority to do something? Can you prove you've been vaccinated so you can board a flight? Can you prove you have emergency medical training so if you show up at an earthquake or a hurricane, you can help? Can you prove that you're allowed to be in a remote wilderness area to study endangered species? This is a big area of research where generally called identity and access management, tools being developed to enable you to prove on your smartphone with encrypted information about your credentials to speed approval to get you access. It's also an important growing field of systems analysis, along with the many others I've talked about. So thank you for your attention, and I turn it back to Igor.
Thanks a lot, Fred. As we just have known from this brilliant talk, a mathematical background of systems analysis is not striving to some one unified mathematical toolkit. Rather, it is a wide set of various tools inherited mainly from the operations research area, which in fact may be considered the predecessor of systems analysis, with its objective to optimize behavior of large-scale systems. In turn, one of the most powerful and valuable areas of the operations research is the games theory, and there is a lot of interest regarding application of this theory to problems which are so far associated with systems analysis. So I think it would be of great interest for all of us the talk of Professor Abraham Neyman, being one of the world's leading experts in this area. Please, Abraham.
Can you see my just a moment? I'm trying to upload the slide. Can you hear me?
No, I don't see. I hear you, but I don't see your slides.
Okay, let me try to do it again. Okay, I'll close. Reconnected. Let me now try again to share the slide.
Now I see your face, but I don't see your slides.
It is grinding trying to upload it. Let me.
Something unexpected.
Let me. I think it's trying to bring the slide, since it's just one slide, which is a flow chart. Let me start talking without the slide, so we don't waste too much time. And I would like to start with saying that game theory has remarkably many tools, both applied tools and theoretical tools that are being used. And I was decided, since we are speaking here of system analysis, to pick a topic that is calling for research and incorporation of some of these game theory tools. And this issue is the transformation to autonomous transportation, autonomous cars, etc. So right now we all know that there is a lot of global effort to develop autonomous cars. And the question we should ask ourselves is, how would the world transitions from the current situation where most cars are being driven by human beings to the stage in which most cars will be driven by autonomous cars? And where is game theory entering here? Because if it's an autonomous cars, you could decide how it behaves. If it's individual driven car, it is obviously its decisions will be made by the individual optimizing his own benefits. And if all the cars would have been autonomous cars in the streets, then it is very easy to increase drastically the roadway capacity, because the distance between cars, because they will communicate between themselves with the 5G and each one will get and send signals from one to the other, they could reduce the distance, and the start of movement of all the cars at the traffic light could be essentially simultaneous. The question is, what should we do in the transitions when we are moving, and let's say at some point we are 50% autonomous cars and 50% individually driven cars? How should we handle it? Do we have any tools to try to design the system in such a way that the welfare will be maximized? The time of driving on the road will be minimized, the capacity will increase, etc. So if you hear me, can you state one type of difficulty? What will happen in a traffic light in which you have both human-driven cars and autonomous cars? What will be the difficulty there? I see my slide is not coming up yet, but can you hear me?
Yes, we can hear you.
You can hear me. Okay, so if all cars at the traffic light are autonomous cars, then they all can move instantaneously. When you have the green light, they could all move, and basically, even you don't have to have a traffic light. They could all move in all directions, and there will be a central control that will tell each one at what speed and at what and where he could turn and where he cannot. But if you have some of the cars are being driven by human beings, it will be impossible. So the question is how to design. What is the model? What is a game theoretic model that can try to, and analyze and being applicable to this situation? And this is the model of a stochastic game, but it still has several shortcomings that will be needed to overcome in order to apply it to this type of situation. In a stochastic game, you have a state variable. What is a state variable in terms of the movement of the cars in the system? It is basically a description of the positions of all the cars on the road and the direction where they want to get from point A to point B. It's a very huge data. Making optimization with such a huge amount of data, both of the individual side and of the autonomous car, which is somehow easier because it will be controlled by a central computer or by a system of computers, then you have to make, each one will have to make the decisions. So the decisions that the individual will make will generate a transition of this state variable. And each one will take the decision that will take into account his short-term benefit as well as the new position of the entire system. But the entire system will be a system that will describe both information that is relevant for his own decision, as well as information that is relevant for the total welfare of all the traffic that is moving from one point to the other. And therefore, on top, so this type of a model is called the stochastic game. But doing all this optimization, you have to be able to do this optimization with a limited amount of memory and computational resources. Some limits apply to the individual drivers and some much larger limits to the autonomous cars, because they will be equipped with very powerful computers and also will have system aided from the central computers for information and for the decision. So you need to study stochastic games not only with an unlimited computational and optimization resources, but with limited ones, and that you have to be able how to handle. And finally, as was mentioned, now the amount of data will be extremely huge. So you have to incorporate all these type of studies and to enlarge the study and the domain of stochastic game into cases by which the state variable of a stochastic game is a very huge state space, including many parameters. Some of the parameters will be parameters that are relevant for the individual optimization. Some of the parameters will be relevant for the general, for the central system that will control how the autonomous cars are driving with the full objective of increasing as much as possible the road capacity, obviously minimizing the number of accidents, etc. Any questions? So
thank you. Thank you.
Maybe just to summarize, the issue is autonomous, the transformation to autonomous car drivers. The tools in game theory are stochastic games. One of the tools, there are additional tools, but for some of the aspects that I described is stochastic games, where the optimization is being performed with limited resources and when the data is extremely huge.
Thank you, Abraham. Let me make some comment, short comment. Everybody who made an attempt to model critical infrastructures know but the transportation infrastructure is the most complicated and hard case. Energy infrastructure, healthcare, information, they're static. But if we want to model and simulate the transportation infrastructure, there is much more complex and computational complexity and dimensionality and so on. So thank you for a very interesting talk, which of course is of great use for all who deal with modeling of transportation infrastructure. Thank you, Abraham, once more. So now we have a much broader view on mathematical background of modern systems analysis and its applications. Some new opportunities in this area arise from the attempts to apply to modern systems analysis problems. Some are relatively fresh and novel tools, such as agent-based modeling. And there is a very positive experience of IIASA scholars led by Dr. Ryonsky, who have developed several valuable models for solution of non-trivial and complex practical problems. Please, Elena.
Thank you. I start to share my slides. Can you see them now?
Yes, we see.
Great.
All is fine.
Thank you. Thank you very much. Yeah, it's a big pleasure and honor indeed to present a little bit of our work in this very short presentation. And my talk actually resonates very well with the first talk by Professor Fred Roberts, who highlighted all these different alternative and complementary methodologies that are being used in systems analysis. And I just really, without coordinating, actually prior coordination with Fred, actually I would really continue on that and give in this talk a little bit of a general introduction, but then also 3 examples of specific research projects that we had at IIASA that really demonstrate the power of those methods. Before I do this, let me show you this slide, and many of you know this framework of VUCA, where these 4 letters, VUCA, stand for volatility, uncertainty, complexity, and ambiguity. And arguably, these are 4 major challenges to the decision-making of our current times. Yeah, when we think about public policy planning or challenges being faced by different decision makers at different levels, very often they are facing these 4 fundamental challenges. Yeah, volatility, I think we all understand, and now with COVID-19, we don't need to be convinced even more that volatility is really affecting us very, very strongly. Uncertainty, here we also mean both ontological and epistemological uncertainty that decision makers are facing. Complexity, of course, is ever increasing, and especially in the last decades, the global complexity of economic processes, of social interconnections, has really increased very significantly. And then ambiguity here refers to multiple stakeholders that are typically involved in any complex process. And not only every stakeholder has different interests, multiple interests, but also they are not always fully aware of their own interests and their own preferences. And even more so when they are aware, or to the extent they are aware about their interests and preferences, they are actually not willing to, in most cases, they are not willing to reveal those preferences. So all of that creates really big challenges for researchers who would like to support decision makers with systems analytical methods, tools, and insights. And that is what we are trying to do with IIASA, at IIASA. We come with this realization that once we are using actually models as a major tool of systems analysis, and by models I really refer to a very broad concept. A model is actually any simplification of reality that helps us make decisions. It doesn't have to be necessarily a mathematical model, but of course, in the IIASA's research, we mainly deal with mathematical models that are expressed in mathematical language, but it can also be any simplification of reality. When we want to use models to support decisions and decision makers, those models have to be agile. Of course, they have to be reliable and relevant, but this agility element has really, so the importance of having model in this kind of agile manner that you can mobilize in a way that is most useful to the challenges that decision makers are facing in that particular moment is really becoming more and more important. And those models really have to be able to deal with those 4 challenges. And what we are observing is that, of course, a lot of advances have been made in the course of the decades since modeling started to be used to support decisions. A lot of advances have been made, of course, to make those models really serving the purpose of being able to deal with volatility, uncertainty, complexity, and ambiguity. And Fred in the first talk alluded to some of the examples of those successes, but still, it's really important to realize that very often, in many cases, we are using the mathematical approaches that have been designed for a different purpose. They mainly were designed to meet the challenges and needs of physics or mechanics, which are very different from those challenges that we are now talking about. And therefore, even though, as I said, so of course, a lot of advances have been made and methods are becoming more and more suitable to deal with those challenges, still there is a gap, and this gap really we have to work on that, and that's the ambition of the group that I'm leading at IIASA, to make methods really be suitable to deal with these 4 challenges. And so here I also want to show this slide and remind ourselves that when we use models, it's very important to remember for what purpose we actually want to use the model, and really use models for the right purpose. Yeah, so this, for example, gives a list of different purposes, and in this case it's 16 plus 1 from this quite famous paper of Joshua Epstein, who is the founding father of social simulations, artificial societies, agent-based modeling, and this field. So he reminds us that there are all these different, really different purposes of modeling, and prediction, and he really puts it as 0. So it's of course the most obvious one, but it's not the only one, and may not even be the most important one for some specific challenges and situations. So we will not go through the whole list, but some of those purposes I like in particular. For example, models are really important to explain new phenomena that we now see actually with COVID-19, the proliferation of these modeling exercises that are using this relatively simple compartmental models, such as SEER model and all the extensions, in order to explain the dynamics, yeah, not to predict, but explain. So, but models can go further, so they can do all sorts of useful things, such as, for instance, discover new questions. They can illuminate core uncertainties or demonstrate trade-offs and suggest ways how to harness efficiency. And finally, more into the kind of social sphere, models can be used to discipline the policy dialogue. Yeah, so it's really important when we develop models and when we use models to use them with the idea in mind for what purpose, or when we develop it for what purpose it's actually being developed and how it will be applied. So after this general introduction, here I come to these 3 examples through which I will go very quickly. One example has to do with agent-based modeling. And it suggests ways to deal with this volatility challenge and complexity challenge. The second example will have to do with another method that is called stock flow consistent models that also helps us deal with dynamical systems and systems that exist out of equilibrium. And then the third example will have to do with dealing with uncertainty primarily through stochastic programming, or what we called risk-adjusted optimization and robust solutions. So in the first example, I want to show very quickly an agent-based model of people's behavior. In this case, we talk about pro-environmental behavior and how to, so the question is how to stimulate, how to provide incentives for people to switch to more pro-environmental behavior. And what has been done in this work is that an agent-based model was built that represents dynamic interactions between agents, which are people in this case, and the environment, and also agents with each other. And what is important is that agent-based modeling allows us to model decentralized decisions. And that brings these models much closer to reality than other types of models. And therefore, this kind of way of modeling often helps to increase trust in models and therefore increase the uptake of the results that these models provide. So in this particular case, what is being done is that people's behavior with respect to certain pro-environmental or anti-environmental actions is being modeled, and this behavior is assumed to emerge as a function of so-called affordances. So these are the means that allow people to actually exercise pro-environmental behavior, but also social learning and excuse me, it goes in the wrong direction, and habits. And so here, for example, we can see one result that such models produce in this particular case. It's in a stylized model setting. This means that this model is not, in this case, is not calibrated to any specific data or to any specific case study, but it considers this phenomenon as a general phenomenon of this pro-environmental behavior. So what we observe is that if we increase, so on the x-axis is if we increase the proportion or the amount of pro-environmental affordances, which means the means to exercise pro-environmental behavior, we actually see that the proportion of people who do exercise this pro-environmental behavior is increasing, of course, but it's increasing in a highly nonlinear manner. So what we can see is that when the affordances are relatively low, so in this area, so the people who choose to behave in a pro-environmental manner is increasing, but is only increasing slightly. But then we come to this area where this increase is very sharp, is very steep. Yeah, so there is some critical area or some critical range of the values of these pro-environmental affordances, in which this dynamics really becomes very, is developing very rapidly. And then we quickly get to that new level where further increases of affordances, of course, further increases the behavior, but already not so much as it did in this area. Yeah? So this highly nonlinear sigmoid function that we are observing here is a very important insight for those who want to plan those affordances. It means that it's really important to know where in this region, in this area, the current situation is, because if it's somewhere here, this means that one really has to invest a lot to achieve a significant behavioral change. But if we are already close to this transition period, it may be that one only needs to invest really a little bit to get a very significant effect. Yeah, so this kind of non-linearities is very important, and they are very typical for agent-based models, where the very simple behavior at the micro level actually emerges to the macro level and creates this kind of non-linearities. So this model that I'm talking about here was not only applied in this kind of stylized setting to come up with qualitative results and insights, but it was also applied to a specific case study. In this case, this is bike passes in Copenhagen. Maybe now it will be a little bit clearer what is implied by this kind of affordances. In this case, affordances are the bike passes. Actually, it's a length or the capacity of the bike passes, and that's so you can see similar shapes of plots here. So the model was able to reproduce the past dynamics of how citizens of Copenhagen actually started to use much more bikes rather than cars when the affordances, which is the bike passes capacity, actually increased through the investment of the city. So that shows us that this kind of nonlinear effects really do happen in reality, and therefore again, so this kind of models can really be helpful to support decisions where we really need to represent this kind of decentralized behavior of many different agents. I move on to the second example, and here I want to show stock flow consistent models of economic incentives. And as I said, so this aims to help us understand and provide recommendations on how to manage complex systems such as our current economies. In this case, the stock flow consistent models based on data from balance sheets and transaction flow matrices, and they allow to simulate out of equilibrium dynamics of the economy. And what is important is that these models really strike a balance between complexity and kind of traceability of the models. So they are sometimes referred to as medium complexity models. So they on the one hand, they do represent a necessary level of details. At the same time, they are still traceable, and one can still oversee the model and also understand which phenomenon happens because of which specific details or interactions in the model. So in this particular case, we look at the following question. So everybody knows that this discussion around carbon tax has a lot of complexities, has a lot of feedback loops that it implies. So the question is how the carbon tax can help us overcome the climate change problem, and that how it can support transition to renewables. And here, an important phenomenon, an important feedback loop is taken into account, and that is the so-called sentiment. So what this model shows is that banks' anticipation through stronger climate sentiment, so if they take the sentiments into considerations, that the climate-aligned policy can actually smoothen the risk of financial stability and foster green investments. So these feedback loops that exist between the climate sentiments and the bank decisions, as we can see on this plot, can actually help us sort of show the efficiency of the in this case of the carbon tax policy. And now I move to the third example and come to dealing with uncertainty. As again was already discussed earlier in this session, uncertainty is really everywhere, and decisions that ignore uncertainty most likely will not be the best decisions that we would like to take. There are different types of uncertainties, of course, and then there are different ways, therefore, how to deal with uncertainty. In this case, we are dealing with, one can say, a relatively simple case, and this is when we can describe uncertainty by a probabilistic distribution. Obviously, this is not always the case, and there can be, and there are a lot of examples where we have deep uncertainty, as it's sometimes called, when this cannot be done. But if we have the situation that we can associate distribution, a probabilistic distribution, with the uncertainty, then one can use what is called stochastic programming in order to improve our decisions through this risk-adjusted optimization. So sometimes it's one way of doing this is using so-called chance constraints, when we require that those constraints that we care about should actually hold with a certain probability. Yeah, so we allow that constraints actually may be violated, but this probability of their violation should not be too high. And usually that gives a more realistic kind of, or models that apply this approach provide a more realistic advice and policy options, rather than deterministic models that just say the probability, the constraints really must hold true. Very often this kind of solutions that come out of such approach are too costly, and the relaxing of this constraint can really be helpful. So in this case, I want to show very quickly an example of a system that integrates food, water, and energy sectors, and therefore called food, water, energy nexus model. There is no time to go into details. And what this model does is that it can show us how, depending on how much we are ready to relax this constraint, how much our optimal solution can actually change. In this particular case, we look at one province in China that produces a lot of coal, and the coal production requires water, and at the same time this province is actually quite scarce in terms of water resources, and there are also competing sectors for water, such as agriculture. So the question is, how should they manage their very limited and very volatile water resources that are available in order to support these both sectors? And the goal of the decisions that the leadership of this province should make is to meet certain self-sufficiency requirements, so certain food and energy security targets. Yeah, this means that with a certain probability, they would like that a certain amount of food and a certain amount of energy is produced domestically. And so depending on this probability, and the probability then translates into policy options such as taxing and subsidies. Actually, we can show that, for example, here in the round brackets, the percentages are these probabilities, so these self-sufficiency levels. So they can see how much of that self-sufficiency we can achieve depending on these fiscal instruments, which are summarized here as penalty cost term, but actually in reality they translate into taxes and subsidies. So how much of the self-sufficiency can be achieved depending on these fiscal instruments that can be applied. With that, I come to the last slide where I have a few general remarks summarizing what I just said. Agent-based models can be a suitable tool for modeling behavior and emergent phenomena. Actually, it's quite costly, and the validation is challenging. Everybody who is doing agent-based modeling knows this very well, but nevertheless, it's a very powerful tool to represent behaviors and especially bounded rationality. Intermediate complexity models, such as stock flow consistent models, can be instrumental to explore a new phenomenon. So we saw the example of the carbon tax for illustration here. Risk-adjusted optimization enables the derivation of solution options that are not so sensitive to input uncertainties, in case we can represent uncertainties via probabilistic distributions. And what follows from that is, of course, as also was said by the chair of this session several times, we cannot have one approach, but a suite of different models of different complexity and type should be used to provide robust policy advice. So it's really the picture that comes from different elements that we as humans put together. So for maybe this will be in future replaced by artificial intelligence, but so far this is we as decision makers or experts, researchers actually synthesize and integrate, but these different pieces of advice come from different models of different type. Thank you very much, and I would be happy to receive questions or comments.
Thank you, Elena. Thank you for presenting the high level of IIASA work in the area of systems analysis, in the area of modeling global processes and global activities. So we have watched three extremely interesting talks on application of classic as well as new generation mathematical tools, comprehensive for description and solution of a wide area of problems of modern systems analysis. Let me affirm, however, that development of an adequate model and following its computations are necessary but not sufficient step in any problem solution. The success of all activities of systems analysts and scholars is dependent finally on how an interaction between them and decision makers from policy and economy staffs is organized, including assistance and advertising from the scholarship side. Professor Salo has a great experience in this topic, acquired during his participation in the Finnish government activities, including that which were regarding COVID-19 response. So it will be a lot of interest for all of us to watch his talk on these affairs. Please, Ahti.
Thank you very much for the introduction. And I have entitled my brief presentation as Producing and Using Model-Assisted Policy Advice, and actually I will be emphasizing the using aspect, given that the previous speakers have wonderfully addressed some of the topics in producing. And my roles in Finland include some responsibilities in the government foresight group, where we have some 12 experts to guide the government in assessing national foresight work, to catalyze new activities and to comment on previously commented one. And in relation to COVID-19, one of the challenging appointments which I did have as a member of the COVID-19 science panel was to support the so-called working group consisting of the chiefs of staff from the different ministries to prepare a plan for the Finnish exit strategy. And this was already in April 2020, May 2020. And for instance, we were asked to provide inputs to the decision whether or not schools should be reopened at that time. And also further to the notion that we are talking about producing research, but in any given country, there's only so much research that can be produced. But we can also look at the question, can we perhaps facilitate the transfer of research from other countries? And in Finland, since last August, we've had a process so-called COVID-19 study review, where we have some 12 researchers, appointed researchers, producing summaries, and my responsibilities would be in the areas of resilience and anticipation. And all of this is publicly available, and it's being communicated to some 1,700 participants, and it's in Finnish, but this is the Google translation, it's readable. So if you wish to take stock of the materials, please feel free to do so. Then some observations. I would say that there's been an unprecedented surge of advanced modeling activity, employing SIR, susceptible, infected, recovered models, soft computing, artificial intelligence, data science, whatever. And what is also notable that some of these studies have had immense policy impacts. The report by the Imperial College on the 16th of March 2020 was one of the key catalysts for the decision to introduce stricter policy measures in the United Kingdom, for instance. But it's good to note that actually some of the countries which have apparently strong or even the strong analytical capabilities have not been doing so well in the pandemic. And one key component in all of this is to realize that it is not only the policymakers who are decision makers. Each and every one of us is a decision maker in terms of our decisions. In terms of the decisions which we take. Can you please, there's someone else. Okay, and also when seeking to promote the transfer of research from other countries, it is good to remember that any given results need to be interpreted with care, because they've been developed for different contexts with their specific contingencies and peculiarities, and therefore they cannot be adopted as such. And now actually I would like to put on my hat as an educator in systems and operations research, and for purposes of excessive simplification, this is what I tell my students. These are the cornerstones of systems and operations research. We're looking at systems, typically complex ones. We seek to understand them better by building models with the aim of supporting decisions. And in this context, there are challenges for delivering model-assisted policy advice at this level, relating the system as such to modeling. We have, especially in the early phases, how does the virus spread? It wasn't really known. And at present, there are some new variants arising. So the very properties which they have in terms of their impact on health are not very well known. Then when we look at the interface between decisions and models, there are questions as to which one of we can build so many models, that actually there's a potential danger in that the decision makers will be confounded and confused as to which one, because the models may be telling different stories. And also the models may have different scope. And as a result, the implications beyond the intended scope or defined scope may also be of interest to the decision makers, yet they are not covered. And finally, we come to the interface between the actual decisions, policies, and the system. So do we really, can we be confident in expecting that people will obey restrictions? And how can we address trade-offs between different sectors of the economy or different regions? So all of this is quite complicated. And I would actually argue that there's a space for risk management, but the system, all this full range is so complex that there's a need for collaboration among the many stakeholders. And here I would actually point to one of the discussions which was quite influential in Finland. The president of Finland, Sauli Niinistö, he annually organizes these so-called Kultaranta discussions. And there was a process, and all of this was done online, virtually, using virtual tools. And the appraisal of the economic impacts in connection with those discussions was facilitated by a company called Ngos. And I'm pleased to know that actually that company has emerged from some of the complex and sensitive peace mediation processes which were facilitated by Crisis Management Initiative, established initially by the former president Martti Ahtisaari, also the Nobel Peace Prize laureate. And how did this company come to be? Actually, it sort of relates back to some of the research we did some 10 years ago at Aalto University, together with Villa Brummer, now the program director of a CMI. And as a result, there's been a maturation of the methodologies from methodological research at the university via further enhancements at CMI. And actually, one of the questions which I would like to pose, in a sense, is that is it the case that actually crises are something which spur the development of new methodologies? And if I think of one of the most significant previous crises, so some 12, 13 years ago, we had the financial crisis. And therefore, there was a huge interest in seeking to understand how the financial sector is, what kinds of interdependencies are there. And one of the companies which in a sense also links back to our research here at Aalto University is that there's a company called FNA, which has been quite successful, as in evidenced by the numbers above. But again, that too links back to the work with which a former student of ours had first at the Bank of Finland and then at various central banks. And this is the, let's say, the migration path. And here my key point, in a sense, would be that as researchers, we are oftentimes incentivized to produce more and more of research. But actually, from the viewpoint of enabling the uptake of that research across the broad spectrum, it should be a landscape where we actually have some companies which then take some of these activities forward. And I was also very pleased with the comments by previous speakers that we do need improved methodologies, and this is also the area. We had a paper in decision sciences, but developing methodologies. So I would say that they're an ever-pressing key need to produce advances in dynamic optimization, stochastic optimization, and so on. And finally, I would conclude with a few reflections. So I would say that there's an ever-present, if not ever-growing need for methodological advances, there are exciting frontiers at the interfaces between decision and policymakers, systems and models. And I would say that actually the elements by which the human component, people component, needs to be embedded. I've been very pleased to hear about the agent-based modeling approaches in linking to the model, so that actually the models, in a sense, will be shifted as if it were from the third place to the second one, so that they actually do become the kind of a focal lens which really helps us understand systems better. And finally, 2 remarks I wish to stress: that the behavioral assumptions which we make in seeking to capture the essence of these complex systems, it also needs to be understood and accounted for in producing and using policy advice. It is oftentimes the hardest one to get a good hold of. It's about people, and people are sometimes unpredictable. And also I would argue that sometimes the development of these novel methodologies in practice, it may call for the iterative incremental changes in organizational practices, and therefore it may take time. It doesn't happen overnight, as exemplified by the 2 companies I mentioned previously. So thank you very much, and I look forward to our discussion.
Thank you, Ahti. Thank you for presenting us that achieving a compliance between models treated by system analysts and real policy making is not so simple. And that we must keep in mind. And you're right saying it is a very iterative process, especially in such hard conditions as we had during COVID-19 pandemic. And I agree with you that some countries having outstanding analytic capabilities in all senses of these words dealt very hard with this pandemic. So, as we have learned from the bright talks of our panel speakers, there exists an evident optimism in the assessment of future efficiency of systems analysis as mathematics of the 21st century, and as it is often referred. I do share this optimism and should be so ambitious to affirm that future achievements of systems analysis in complex problem solving will depend on its convergence with 2 intensively developed areas, big data and artificial intelligence. Big data, in fact, is a new way of thinking of large-scale systems operation, and those who would be able to implant the big data tools and technologies to systems analysis toolkits and frameworks would be able to develop and apply much more close to reality and adequate models of real systems and problems. From the other side, implanting to the aforementioned frameworks tools originating from the artificial intelligence and machine learning, especially that of the knowledge engineering area, provides much more rapid and flexible modeling. That is very, very actual, as I said, when we need to have many iterations to achieve the most adequate model. We have saw it just now from the Dr. Ryonsky talk and Professor Salo talk, where such tools made agent-based and origination from the multi-agent systems area as one of the advanced AI technologies were successfully applied. And also application of the AI-based approaches would simplify an interaction between systems analysts and decision makers, providing easy and rapid creation and maintenance of knowledge bases reflecting system structure and logical operation. So I think that our panel discussion was very useful for all of us, broadening our perception of systems analysis and its frontiers. Let me thank all panel speakers, Fred, Abraham, Ahti, and Elena for their brilliant talks, and for time they have spent preparing their talks and participating in our panel. Thanks to all who have watched the panel via Zoom and YouTube. And thanks a lot to the IIASA staff, especially to IIASA Director General Albert van Jaarsveld, for organizing this remarkable event. Wish you all to be healthy and wealthy. Please save yourselves in these hard times. Good luck.
Thank you.
Thank you for organizing this.
Yeah.
Thanks for great sharing, Igor.